slotted terminal adaptive collections. So it's a type of anti-collision protocol like slotted alvoha or binary tree. Okay. So it is designed to read tags efficiently in slots while reducing the collisions. That here is the STAC slots. This diagram is divided into two parts, that is STAC slots and then STAC protocol state diagram. Okay, the first one is STAC slots. Here the slots are numbered as slot 0, 1, 2 and up to n minus 1, correct? So the reader organizes the communication into these time slots. So each tag will pick a slot based on matching rules to be responded. Okay, the next one is protocol state diagram. Here the enter field give the information about when a tag comes into the reader's interrogation zone, it enters the ready state. Okay, then comes to an ready state, that tag waits for the reader's command. It starts a round by announcing a slot frame. So two possible cases here. The first thing is mask does not match. That means tag goes to destroyed or ignored for this round only. Okay. Second thing is mask matches, which means tag participates in slot selection. Then comes to an begin round, that means mask matches. If the mask matches, the tag chooses a fixed slot, that is deterministic, not a random. So after the responses, if the tag slot matches the CRC check, so it enters the slotted read, which means success state. Okay. Otherwise, it goes back to fixed slot for the next round. Then comes to an slotted read part. Here the tag is successfully read by the readers. After this, it is excluded from the further rounds. Then comes to an destroyed state. If the tag does not meet the mask condition, it is discarded or destroyed for that round. So in STAC, it uses slot based communication, but instead of random slot selection, tags use deterministic slot mapping. So it reduces the collisions compared to pure slotted alvoha. So it states that ready, destroyed, fixed and then slotted read. The next one is EPC UHF class 1 generation 2. So here it is an international standard for RFID tags and readers. It is specified by EPC Global and later it can be adapted as ISO standard. So it is the backbone of the modern RFID applications like supply chain, retail and logistics, tolling and then access control. So its features, it's based on their frequency band, modulation in the sense it is an encoding, right? It may be an forward or backscatter or Miller coding like that. Then comes to an anti-collision, it's purely on singulation while using slotted alvoha. Then tag memory banks, it can be categorized into reserved, EPC and then user memory. And their tag commands, its inventory commands or access commands and then security commands it's based on different applications. Then comes to the performance, it just supports high speed tag reading and low power consumptions also is possible. Then comes to when security and then privacy, it can kill passwords and it access the password. Some implementation use for an additional encryptions or privacy, it's also here. These are all the inventory commands: query adjust, and ACK, select command, and access command. So this is the protocol state diagram for EPC Gen 2. So finally, when tag enters into the readers, which means RF field, in the sense its an power is on. The tag moves into the ready state. Then comes to an ready state. The tag is awake and ready to participate. Here it moves into the attribute. Then comes to an arbitrate state. Tags randomly picks slots using some slotted alvo or queue algorithm like that. So this avoids collisions when many tags respond at once. When its tags is turned, it moves into the reply. Then comes to an reply state. The tag responds with the temporary 16-bit random number. So if more than one tag responds at the same time, a collision occurs and its process and restarts. If only one tag responds, the reader can acknowledge it and the tag moves into the acknowledged state. Then comes to an acknowledged state, the reader sends an ACK command with RN16. So that tag recognizes the RN16 and it sends back its full EPC identifier. That tag then moves to open. It comes to an open state. The tag is now open and it can be accessed. The reader can issue reader or write or lock or kill commands. If the reader provides a valid access password, the tag transaction is to be secured. If no password is set or only valid RN16 is present, means the tag stays is open. Then comes to a secured state. In this state, the tag requires an access password for sensitive operations. For example, writing EPC memory, locking banks, or killing the tag like that. So this is the protected mode for enhance the security. Then comes to a kill state. If the reader sends a valid kill command with the correct kill password, the tag is permanently disabled. Once killed, the tag cannot be reactivated. So any command sent afterward is ignored as shown by any command that is killed. So this diagram shows how an EPC Gen 2 RFID tag transition from being powered on through anti-collision and identification to either being accessed normally, secured with the password, or permanently killed. So I have to conclude that troubleshooting RFID tag communication requires systematically checking the tag, reader, antenna and environment and software settings also. So most issues come from orientation, interference or misconfiguration.